I'm in. I'm going. I'm gonna buy a parka or something. Oh no.
Okay, guys, let's go ahead and get started today.
Even though it's like ice.
To start with here, we can just do a really quick recap of what we covered on Wednesday. So we were talking about basically reflection seismic processing, and we were talking about how you can move kind of from this type of a record, which is known as a common shot gather, where you have kind of your source point here, and you can see your energy and your direct waves kind of traveling outwards from it, and then you start to get your reflections down here that look like these hyperbolas. And then we basically translate that into one of these common midpoint gathers, where we look at all of our different shots, and we find all of the different pairs of shots and receivers that share the same kind of reflection point at depth, or the same midpoint. We combine all of those measurements together into this common midpoint gather, and on those we can we fit this hyperbola here that corresponds to, we're fitting the hyperbolas in that record that correspond to each of our reflections. We find kind of our stacking velocity, and that allows us to kind of flatten the hyperbolas into horizontal traces if the reflecting layer is horizontal. And from there, we can then kind of stack all of these traces in our common midpoint gather, and we get kind of a concentration of energy basically along that reflection point, where they all of the peaks from our reflection line up, and then hopefully in the areas where we have noise, kind of that random noise kind of cancels out, and so we get basically an amplification of that reflection event as we stack. And then from that guy we get out this individual trace, which kind of shows our different reflections, and each one of these individual traces that come out of this common midpoint stack can then basically go into this profile here, where each of these lines and each of these offsets kind of marks our common midpoint location, and we build up this profile that shows our reflections off of the different layers in the subsurface. So first of all, does anybody have any questions about that process, or we can move on? No? Okay, so the natural thing then to do, once we have kind of this section here that we've applied this NMO correction to, we now have what are basically these zero offset traces where our source and our receiver is deemed to be at the same spot, and we have like this series of reflections off of these interfaces in the subsurface. So one thing that you can then often think about is, are those reflections really showing up in the right spot? So like spatially or temporally, are those reflections actually where the interface is in the subsurface? And that's important because we are making this assumption that our source and receiver are at the same point. So any reflection that comes back has to be hitting the interface at a 90-degree angle and coming straight back up to the same point. So if we don't have a flat line layer, like if we have a dipping layer, like is here in this picture, the point that we're reflecting off of and coming back to isn't directly under the source and receiver anymore. Because in order to hit that interface with a 90-degree angle, it has to be kind of this pathway here. But the way our processing has treated it is as though it's right underneath it. So the actual dip of that layer that shows up in our seismic section is going to be underestimated. So there's a simple relation here that we can use to go from that kind of apparent dip back to a true dip bed. So in the case of just a horizontal but dipping bed, it's a pretty easy correction to do to shift those reflections into their true location. But maybe we have an interface down there that is something like this. So now we have kind of like a roughly flat line bed here on the sides, but we have kind of this synth line in the middle. So if if we were going to say we're starting here at point A, and we've already done like our NMO correction to this data. So now we're going to have like energy that's going to come out of this. It has to hit this interface. So we have downgoing energy from our source that comes down, and then we have an upcoming reflection that comes straight back up and returns at A at time, like we'll just call it time, I don't know, let's label this interface, let's just label this point here Z. So this reflection here, we could plot over here underneath A, and so we're going to get a reflection back, let's say, that sits here, and this is at time AZ. So that's the time it takes to go from our shot at point A down here to Z and then back up to A. But now when we move over here to point B, our ray can't, like if our energy, we do, so basically you still have energy that's propagating outwards like this from your shot point. So you actually have kind of rays of energy that are coming in at all angles. But there's only 3 of them that are going to be able to reflect back up and return to this exact point. So we're going to see basically 3 different arrivals from this interface, this one single interface at B. Does anybody want to kind of help me guess here where those reflection points are going to be? Because if it comes straight down, it's going to hit the interface at this angle here, and it's got to reflect back at basically the same angle that it hit the interface. So you're actually, like, the reflected ray is going to come off this way if it just comes straight down. If I had like my little normal to the interface here, it would kind of leave at the same angle it came in at. So this energy that came straight down is going to reflect off that way, and it's not ever going to get back to this point. So there's kind of 3 points on here where we could say that it was pretty much orthogonal. So like if it came down there at that angle, it could come back up. Similarly, there should be 2 of them over here. So we got kind of those 3. So I don't know, we can label these Y, W, X if we want to. And so now we have these other times. So if we look at this time here is going to be a little bit greater than this time over here was. But it's going to be less than either of these 2. And this guy here is going to be shorter than this one. So TW or TBW is going to be the longest one, kind of. So if we come down here, we're going to have one time down here, kind of. We're going to have probably like another one up in here, and then a third one that's maybe up here like this. We'll put these 2 a little closer together. Is everybody okay with that general idea? Yeah? So now what happens if we have a shot directly at C? Where are those like orthogonally reflecting rays? Where are those going to strike this interface and come back, straight back up? Any guesses? Don't be afraid to throw out ideas. Anybody? Yeah?
Into the ground.
So where along this interface are they going to need to come down to? Yeah, good. So yeah, it's going to come straight down here. If we're assuming C is directly above the base of our synth line, then we're going to have one ray that is coming straight down at this point, and then coming straight back up, and then they're going to be kind of evenly distributed here. And I think it could be something like this, and something like this, just kind of like you said. So then we know that these 2 points, or these two, because of just the symmetry of the way we've laid this out, if things are symmetric, then these two are going to have the same time, because it's like the same length of path, and then this one here is going to be longer, right? And that one is probably, yeah, he's probably, so we're going to probably have something sitting like this, and then maybe something like this. And then, so if we had another point over here, and another point over here, we know that those would just kind of be reflections of these guys across this midpoint, right? So we could also, we could just kind of mirror them across to kind of draw what we have going on here roughly. Right? So then if we came in here, like we're going to have a reflector over here that is pretty much flat line, right? We look at our time versus distance plot on either side. We're basically going to have these horizontal reflectors if we've done our NMO corrections correctly. So these guys are in the right spot, right? So we got a horizontal layer over here. But now, when we start to get into the central area where the anticline is, what we're going to basically get is something that comes through here, comes back up here. We're going to kind of have something that looks like that when we end up tracing out all of our little, like if we had, so I mean this is assuming that we have like receivers at each of these points and we're measuring all these reflections. And this line and this time versus distance or time versus offset plot basically just is trying to mimic kind of this profile of data. So wherever we see one of these like reflection arrivals here, we have this line here. So if we were thinking about this as like our little seismic traces, we would have things flat, and then maybe we would have like a little arrival of energy there, right? And then so then when we got here, we would see something that looks like this, right? We would have some sort of a reflection event and flatten out, right? So I mean, unless you kind of know what you're looking for, then this kind of, they call this like a bow tie reflector kind of thing. We have this interesting shape of reflection, and it really doesn't look anything like our syncline that we're actually reflecting off of. So that's kind of what that's what this whole process of migration is about. We're trying to correct the location of these reflections in either time or distance, so that they basically represent the true surface that they're reflecting off of. And so for something like this, I mean, it can definitely get more complex. Like that migration process is going to be more complex than we're going to focus on. But we can just, we just kind of went through this and showed that that's the type of reflection we get out of it. And we can see this in field data. So here, if we're looking at this top section, this is a section that has been, or a profile that has been NMO corrected. And you can kind of see down here at each of these arrow points, you can kind of see the start of some of these reflector guides that kind of look like that bow tie that we just sketched out. Maybe a little hard to see because it may be small. But then when you look down here in this bottom section, this is a section that has been time migrated. So our axis here is still in time, hasn't been converted to distance. But you can see these little synclines in this interface down here. So we have this interface that has probably had some channels or something cut through it, and inside these syncline-like structures. And we can actually see those in the migrated section now. They don't look like these bow tie features. So that's all we're doing with migration, is basically correcting the spatial and temporal location of basically these reflectors so that they mimic the true structure that they're reflecting off of. That's kind of our goal. Yeah, so I guess we're going to move, that's all of the time we're going to spend kind of focusing on migration at this point. So then I guess many of the sections that we've shown have just been displayed in terms of offset versus time, but you can also convert your time axis to distance, so you actually have an estimation of depth where these reflecting layers are. And the easiest way to do that is just to use that stacking velocity, basically, that we used for the NMO correction, because that's kind of giving you what the kind of average velocity is for the medium above that reflector. So if we use that and we know what the two-way travel time is, we should be able to then convert that axis out of time and back into depth, because we have an estimate of the velocity and we know how long it takes to get down to that reflector, so we can convert that into a depth. Does that make sense to everybody? Basic, yep, good. And we should also talk a little bit about resolution, so like our vertical resolution of layers that we might see in the ground. So this top picture here kind of has these three layers that are like roughly equal in thickness. I mean, the middle one may be a little thinner. And we can basically see that the reflection that we're getting off of the top of layer 2 and the reflection that we're getting off of the bottom of layer 2 are pretty nicely separated in time. So it's pretty easy to like differentiate those two and say that, yeah, I mean, this is the top of the layer reflection, this is the bottom. We have like a distinct layer there. If we start shrinking the height of V2 though, and those two reflections off of the top and bottom start to merge together, there becomes a time basically where we can't differentiate the reflection off the top and the reflection off the bottom, and we essentially lose the ability to resolve that second layer. And so kind of there's a criterion that's called the Rayleigh resolution criterion, and it basically, as kind of a rule of thumb, it kind of lays out the fact that you want to have like the separation distance that you kind of ideally want to have between your two peaks of your kind of reflected events here is roughly equal to half of the wavelength. So basically, if you looked at your characteristic like wavelength of your seismic energy that was coming out of the ground, you would look at the peak to trough distance, that kind of characteristic wave, and you'd say kind of what is that distance? And that distance is half of the wavelength. But then in this case, this first reflector is just coming down and coming back up, but the one off the bottom is going down, it's coming all the way through layer 2, and then it's reflecting and it's traveling backwards up through layer 2 again. So basically the difference in the distance that this reflection has to travel, it has to travel all the way through layer 2 twice. So we can relax kind of this resolution criteria that says basically our layer has to be equal to half the wavelength, and we can kind of reduce it down to a quarter of the wavelength. So if our layer is kind of roughly any layer that is thicker than basically a quarter of the wavelength that we're dealing with, we should be able to resolve the top and the bottom of it pretty nicely. So then, depending on the size of your layer and how deep it is, we can kind of, well, especially if we're doing an active source seismic survey, you can kind of decide what frequencies you put into the ground. So you can do, like with a vibra-size truck, you can do a sweep of different frequencies. And if you were looking for very thin layers that were pretty close to the surface, you would make sure that your sweep of frequencies that your vibra-size was putting out was pretty high. So you'd be putting out high frequencies. Those high frequencies are going to give you the resolution you need to be able to resolve small, thin layers, but they're going to get attenuated as they pass through the ground pretty quickly. So you're not going to be able to see deep layers with it necessarily. So basically the thickness of a layer that you can resolve is going to change as a function of depth as well. Any questions on any of that stuff? No? Okay. Okay, there's one more kind of method that we're going to talk about, and it's called MASW, which is basically multiple azimuth surface wave or multi-channel analysis of surface waves, and it's a newer type of method, I would say, compared to these other ones. And basically, what we're doing is we're using some of those surface waves that we didn't use in the previous processing. So like the stuff that came in as kind of ground roll, and we're actually going to try to use those arrivals, those reflections of these surface waves to determine the shear wave velocity of the ground, which is going to give us an idea of kind of its stiffness, basically, is what it's going to tell us about. And so we have, and so this can be done either actively or passively as well. So when you put out your array, you can be recording these surface waves, and you can do it with an active source. So like you're providing the source, like an explosion or a weight drop or a hammer blow. Or you can also kind of collect cultural noise. So like in this picture here, you have like a helicopter, you have cars driving by. So like many times they'll set one of these up along the side of a road, and they'll just record for quite a long period of time, and they'll just let the noise of the cars driving by basically serve as their seismic source. And they'll just record, and they'll kind of stack all that data. So basically what they do kind of is, so basically with these surface waves, the frequency of the data, so they do what is called basically like a dispersion analysis. So the velocity of the waves is dependent on their frequency. So that because of that, they're said to be dispersive in nature. So that's kind of the act that's kind of showing you that each of these different kind of waves, you have like a characteristic frequency of your energy here, and that characteristic frequency kind of has a velocity. And that velocity that wave is traveling with is dependent on the frequency content of it. And so then we can use kind of this dispersion analysis, and we can kind of get a dispersion curve that's going to cut through here. And from that, we can kind of back out a 1D velocity model of the shear wave velocity. And they'll kind of do that. They'll usually put that at kind of the midpoint of your spread. So I think the next slide may kind of show this. It's a little small. Maybe I should have made this bigger. But so basically we have kind of a source of some sort over here, and we have our spread, and our spread is kind of being moved to different locations. At each of these locations, we're recording a common shot gather for all of our receivers, all of our channels at this particular location. And then we're selecting a point that basically just mimics the middle of that spread. So the midpoint distance from geophone 1 to our last geophone. We're kind of picking the middle of that, and we're kind of doing our dispersion analysis to come up with a 1D shear wave velocity profile at that center point location. And then basically we can, since we're in one of these surveys, we're kind of moving our spread along to a whole bunch of different locations. We're then kind of just building up all of these 1D velocity profiles that we've inverted for, and we're combining them into a 2D section and interpolating in between them so that we get like a full section that's giving us the shear wave velocity as a function of depth along that line that we're covering. And so here we can see, I'm not exactly sure what this data was from, but you can see that we have a much kind of lower shear wave velocity up here in this top layer than we do down here for this layer that's at about 10 kilometers depth. And so this type of analysis is really good for kind of like shallower geotechnical types of surveys where you really want to try to assess kind of the shear strength of the near surface soils. I think we just covered most of the stuff that picture would show us. So again, I guess this is just showing that this is showing your common shot gather with, they've basically taken out they've taken out everything except for those surface waves kind of that they're working with. And then we're using the dispersion analysis to get our phase velocity as a function of frequency and get this dispersion curve. And then from this we're sampling this dispersion curve and then basically inverting for our 1D shear velocity, shear wave velocity. This is just another plot of kind of what one of those dispersion analysis curves might look like. So there was a case history, actually, that we went over in your first TBL, where they were in the city of Dublin, and they were basically, they were going along and they were trying to measure the shear wave velocity and kind of map the thickness of glacial till and bedrock under some of these roads. And so if we kind of just walk it through like that basic 7-step framework like you guys did in that assignment, if we look at like the setup, again, we just kind of have this hard till, which they're expecting to have a high stiffness and a low permeability. And then they're also going to have some layers of like cobbles and boulders and things like that kind of above your bedrock. So they just kind of want to map out those regions to get an idea of stability. The main properties that we're working with are kind of our elastic properties. And those are obviously related to the stiffness of the soils and the bulk modulus. And then, so the actual property that we're going to be kind of solving for and having in our inverted sections is this distribution of shear wave velocities. So I guess here, yes, they were doing kind of this roll-along survey, so that just means that they kind of had their source and they had a spread of geophones. They would fire their source and they would kind of move the whole system up a set distance and do it again and repeat. So then they could kind of use each of those sections to build up their profile in the end. So it looks like here they had kind of 24 of their geophones that were all connected into what they called kind of this land streamer. So it kind of acts, instead of having to pull up the geophones, because you're obviously on a road, you can't hammer the geophones into the road. So they had kind of this towed streamer that was probably being towed by this thing here that looks like a tractor. And it's kind of like the streamer, the hydrophone streamer that you'd have in the ocean. All the geophones are just connected at a set offset into this like cable tone streamer that's made behind it. And then you can you just couple, I'm not exactly sure how you do it, but there's a way for at each of your little geophones on that streamer that you kind of couple it to the ground. So that it can record the displacements that it sees. So again, here's just some of the data that they collected. These are kind of some of those surface waves that were coming in. They took each of these shot gathers with the surface waves and they kind of did the dispersion analysis to it to get their dispersion curve. Here's their little dispersion curve that they picked off of this. And then they inverted that for this 1D profile of their shear wave velocity, stacked all of those guys together and interpolated in between them to get kind of this 2D profile of the shear wave velocity. Any questions about the basics of that? There's a lot kind of to that process, and we're not going to expect you to kind of know a whole lot more about it than that. So I guess here, when they just looked at it and they were looking at their final model and started to do their interpretation of it, they were kind of, I think they did, yeah, they verified some things through boreholes. So they looked at their section and they saw these areas of like fairly low seismic shear wave velocity. And they said that those low values were associated with kind of that glacial till unit that they wanted to map. And the higher velocity material at depth, the stuff down here in the black, was their bedrock interface. So again, it's not very deep. They're only looking here like roughly 20 meters deep. But they're able to quite nicely kind of map that interface between the glacial till and the bedrock that underlays it. And you can kind of affect your depth of investigation of the survey a little bit by just kind of changing the frequencies of the shear waves that you're recording. So many geophones kind of have a set band of frequencies that they're sensitive to. But again, if you go to like the lower frequencies, you're going to get deeper information, but you're not going to have as much resolution in your service. Any questions about any of that? Any general questions about seismic stuff? So the last part of this lecture was kind of posted as just being kind of like a seismic review. We can kind of spend some time going over anything that I've talked about or Sagi's talked about in the last couple of weeks that you guys aren't quite sure of. Any questions or anything come to mind? Like,
if the interface is curved like that,
yeah,
same line,
yeah.
how would if in a glacial, does the ray just follow the interface?
Oh, so you're talking about a refracted arrival
Yeah,
on an interface like that. I think it would probably depend. Well, no, I think it would probably follow the interface. Well, that's a good question, actually. I don't think they look at things like that very often, to be honest. Because actually, as it would start to travel and follow that interface, I think, depending on like the angle of this, when it kind of strikes that interface, you're going to get a refraction along this as soon as it hits this interface again. So depending on what angle it came and hit this at, and depending on the contrast, it's going to, like, you're going to get, does that kind of make sense? Like, it's going to hit and travel along here, and as soon as it hits there, it's going to get kind of diffracted. And so I think some of it will definitely come back up to your receivers at that point, but depending on kind of the slope of this and this angle, I think you could almost get another little refraction that kind of just sent the energy traveling off that way a ways, and it might not get to the surface. So that would get pretty messy pretty quickly. Refraction surveys aren't really designed for that kind of application mostly. You start to get a more complicated geology like this, you really kind of need to switch over to the reflection to be able to do a good job of estimating your, I mean, you'll still, over here on the sides, if this velocity is higher than this velocity, you'll still be getting refraction events over here, and you'll still have a good direct arrival from it that you can pick, kind of estimate the velocity of this layer up here from. But yeah, trying to do refraction analysis off of an interface like that would be quite challenging. I don't know for sure how you go about doing that.
I was just wondering.
Yeah, no, that's a good question. Any other types of questions? Anything that you guys have seen in the lab or anything like that you weren't sure about?
So like earlier today, you talked a little bit about the correction on the sync line and stuff like that. Like there's the like the tangent of an angle and the sine of an angle and stuff like that.
Yeah.
For exam or question like quiz purposes, like do we just need to know that this is something that exists that people do, or like is the expectation that we might actually have to crunch numbers or something like that?
I don't think you'd actually have to crunch numbers. I mean, it would be feasible maybe for you to do it for just the dipping interface. If we would have to give you the formula for it though.
Right. So something like that, like where we don't actually like spend time working through it in lecture and lab, it's more sort of like conceptual grasp of it.
Yeah, I would say so. Yeah. Yeah. Anything else?
If you have rock units that somehow like turn themselves vertical, and you still use seismic surveying, now the interfaces are vertical, right? So you will be bouncing.
Yeah. So I mean, I guess just if we just sketch it out, let's say we have our source over here, and we have like maybe this whole sequence of rock units that have been tilted vertically like this, let's say. remember that from your source, you are going to have energy that's propagating out spherically like this, right? But what's going to happen to those rays when it strikes this interface over here? Yeah, you're not going to be getting reflections back from them, right? Because these ray paths are kind of perpendicular to all of these wave fronts that I just tried to sketch there. It's going to hit there, and then any type of reflection is going to take off at kind of that same angle. And it's just going to kind of go back down. And whatever was transmitted through, like, let's say that this velocity here, even if this velocity here is higher and it gets bent towards this interface and refracts, it's just going to travel down that and go down. If it's slower velocity, it's going to kind of kink this other way, pass through here. It's not really going to ever have a way of getting back to the surface. So you're not going to be getting your reflections back to your receivers to be able to see a whole lot. That's going to be a challenging problem. Now maybe you could put in a borehole or something over here, and if you put in a borehole and put a source down in your borehole, then you can kind of be firing stuff from here, and you're going to be able to get reflections off of it. But yeah, you're going to have to get creative. That's a good question. Yeah. Anything else anybody can think of? We still have about 10 minutes left, so I'm at your disposal. Yeah.
Can you just point out specifically on the time distance travel
Yes.
which dots will correspond to which points?
Might be clearer on this because I may not have done that great of a job of drawing it. But here we can just kind of see like our time to go from A to W is right here at TAW. So it just goes down and comes straight back up. And that's, since it's the syncline, that's kind of like our shortest travel path in this plot. And then if we look here at B, looks like we have to X, Z, and Y. And X is the shortest path. It's like Z is the next shortest, and then Y would be kind of the longest one of those. Does that make sense?
Yeah.
Yeah.
There you go, we just covered this, but the multi-channel surface waves, is it, so you're looking at these waves as representation of shear waves from the material, and how is that behaving?
So shear waves are usually going to be, surface waves are often going to be traveling at the shear wave velocity, so they're going to be dependent on the velocity of the ground. They just kind of different. Anything else? Nobody else has any questions. You guys are welcome to leave and start your holiday weekend a tiny bit early. If you do have questions, you don't want to ask the whole class, I'll stick around for a while and you can come up and just ask me. Either way.